Hi everyone, I hope you're really enjoying PyCon US 2021 so far. I'm really excited to be here to present something to you today called Pyjion, which is a project that I've been working on for the last 9 months. And I want to say a big hello to all the international Pythonistas out there, and so pleased that everyone can make it this year virtually, and really look forward to seeing you in the future face to face. In this talk, we're going to cover 5 main topics in a short space of time. Some of these topics, especially the JIT compiler, are very niche technology areas. I'm not assuming that everyone watching this talk is a compiler expert, but I'll really try my best to break down some of the topics. But we don't have that much time. If you find yourself wanting to learn more by the end of the talk, there are plenty of links to follow up with, or you can reach out to me directly. So first off, let's recap from my PyCon US 2020 talk. Why is Python slow? I strongly recommend you watch that talk because it gives some context for why I'm looking at a JIT to solve some of Python's performance challenges. In that talk, I talked about a particular benchmark called the n-body algorithm. The n-body algorithm is a mathematical formula that can calculate the orbits of the Jovian planets, which are Jupiter, Saturn, Uranus, and Neptune. I picked n-body because the Python implementation suffers from an extreme case of some of the causes of its general slowness. If you compare C and CPython 3.9, which is written in C, the execution times are not even in the same galaxy, let alone the same planet. Even Ruby, PHP and Perl put Python to shame on this algorithm when it comes to speed. But it's not those languages I'd like to compare Python against, it's JavaScript. JavaScript is equally dynamic, it has a GC, and it kind of even has a GIL as well. So how is Node.js, which runs JavaScript, so much faster than Python? This is the guts of the Python n-body implementation. To summarize what's happening here, it's looping over a list of tuples, unpacking them, and then performing a number of calculations on floating point numbers. I've highlighted the core integral of the algorithm here. All of the highlighted variables are floats. Something that's important is that Python won't do anything clever with the operators. The compiler knows the order of operations and emits the bytecodes in the correct sequence. It uses a mnemonic that maybe you learned at high school like BODMAP or PEMDAS. The Achilles heel of this calculation is that the result of each multiplication, addition, subtraction is a new floating point object, which then gets dereferenced in the next operation. Let's expand line 74 and I'll show you what I mean. In this equation, Python will run 4 multiplication operations, 2 addition operations, and 1 power operation. The resulting floating point numbers have to be allocated in memory. The native C float has to be converted to a PyFloat object, and then in the very next operation, it gets converted back into a C float. The reference count becomes 0, and so the memory is freed. You might think that memory is fast, but the floating point numbers in steps 1 to 6 in this diagram are all temporary objects, so they get allocated and then deallocated almost instantaneously. So if you think of the time it takes to do that, multiply that by the 500,000 iterations this loop executes, and then again for each planet and then again for each step. It's actually over 1 billion operations of this particular line. So when you add all that up, it adds up to a lot of execution time. If you were to convert this function to a Python module and annotate all of those variables as doubles, it would bypass the temporary object allocations and Python would compile that down to execute about 8 times faster. It does this because a floating point number still fits within 64 bits. So the CPU can keep that on the register and it doesn't have to allocate and deallocate memory from the heap to do the calculation. If you were to run n-body using another JIT, PyPy, it has its own mechanism for removing the allocation and deallocation of these temporary objects. The PyPy approach is super efficient on the CPU, but it does consume more memory. This is a common issue with JITs to have high memory usage at the expense of reduced execution times. So let's recap the conclusion of why is Python slow. There's a temporary object problem. There's the evaluation loop of CPython and the big overhead that has, so tight loops and cycles are really slow. Most attempts at improving the performance of Python come with major drawbacks to either compatibility or platform support. And so having a truly compatible optimizer for Python is actually pretty tricky. The garbage collector is a stop everything collector, unlike Node.js, which does a multi-threaded mark process. And lastly, the theory is that a specialized JIT could help in some scenarios. There are plenty of projects which add a JIT compilation to your Python code, depending on the domain. For data science, and in particular for NumPy, there's the number project. Number is a decorator that you wrap on certain functions with annotations on which underlying types are used. It will then JIT compile parts of the function to benefit NumPy calls. If you're already using NumPy, this is great, but if you're just writing general Python code, it likely won't make any difference at all. It might even make the code slower. Next, there's the Pyjion project, which is a fork of CPython that includes a JIT for some operations using the LLVM JIT engine. Number claims performance gains of 10 to 20% compared to CPython 3.9. However, the drawbacks is that it's a closed source project and that it's a runtime that you have to deploy, install, and support as well. And lastly, the PyPy project, a Python interpreter written in Python, which has a mature JIT that will deliver massive performance gains in many scenarios. The drawbacks with PyPy is that in some cases it's significantly slower than CPython, and also it lacks a lot of compatibility with C extensions. I think there's still a gap here for a general purpose JIT that focuses on compatibility and delivers performance gains to plug some of the pitfalls in CPython's eval loop. This is where Pyjion comes in. Pyjion is a JIT compiler for CPython bytecode. You can pip install it from PyPI, and it's compatible with CPython 3.9. Pyjion is compiled for Linux, macOS, and Windows. It supports 64-bit Intel CPU architectures, and I'll work on ARM support if somebody can buy me an M1. Something I want to make super clear, Pyjion is not another Python interpreter. It works inside CPython 3.9. Pyjion is not a new project either. It was originally presented at PyCon 2016 by Brett Cannon and Dilo Wieland. It was written against the Python 3.6 bytecode. It also only worked on Windows, and it required a custom build of Python because it required PEP 523, which wasn't yet merged and then was later introduced in Python 3.7. It was also written for a JIT compiler based on .NET Core 1.0 beta, which is long since passed. So I have, for all intents and purposes, rewritten the original project over the last 9 months. The design of it's very similar, but there's some fundamental changes which I want to talk about. I know the original project was seeking optimizations through the use of unboxing, integers, and floats, but I've largely abandoned that idea. I don't think the effort is worth the reward, and there are better options for functions which use lots of floats and integers. Pyjion focuses on compatibility. If it runs in CPython, it should run in Pyjion. The JIT startup overhead should be minimal, especially if subinterpreters are widely adopted beyond Python 3.10. This can't be like waiting for a big VM to boot like the Java VM. Beyond enabling the JIT, Pyjion should not require any changes to the code. It shouldn't require type annotations or wrapper functions. I'm assuming that people want to use a general purpose JIT for code that they don't control, they don't want to change. They really just want to enable the JIT in already working code and have it optimized where possible. And lastly, I want this to be able to be deployed anywhere. So if you're using a cloud environment where you don't control the Python that's installed, you should be able to pip install and import Pyjion. This opens up opportunities for all sorts of PaaS platforms where you can add this to optimize your existing code. To understand how Pyjion works, let's look briefly at the components that make up CPython's compiler and execution process. So first you have your Python code. This is parsed in Python 3.9 using the shiny new peg parser. The parser will read your code and understand how and where you've used the Python syntax. It will also throw up things like syntax errors when you make mistakes that couldn't even be parsed. The parsed code is emitted as an abstract syntax tree, or AST. ASTs are very useful representations for the Python compiler. The Python compiler compiles down each function into small sequential atomic commands called bytecodes. These bytecodes are cached on disk in your dunder PyCache folder, and each time Python executes your code, it will loop through the bytecodes and call the corresponding APIs within CPython to bring your code to life. It also does the work of interconnecting with C extensions, handling memory allocation, threading, garbage collector, and quite a lot else. So Pyjion inserts itself between the compiler and the evaluation stages. It will recompile the Python bytecode into native machine code. And it does this at runtime, which is what makes it a JIT compiler. Pyjion will kick in when a function is run a certain number of times. It compiles the Python bytecode into an intermediary language called ECMAScript. ECMAScript is used by the .NET compiler. This is the .NET 5 compiler, not to be confused with, I guess, the older .NET. The use of the .NET 5 JIT is really an implementation detail and in no way helps you doing anything .NET related or working with any .NET APIs. It was selected because the CIL is a good cross-platform low-level IL, and .NET 5's Ryu JIT compiler is a mature, well-supported JIT compiler that it supports Intel CPU, x64, and ARM. So the compiled code is assembly. Well, actually it's machine code, but it's a compiled binary kept in memory. So Pyjion compiles each of your Python functions into executable symbols and caches them in RAM. All of this is really theoretical and a lot easier to explain with a demo. Pyjion is pip installable, so you start off with a Python 3.9 virtual environment. Pip install Pyjion, start up a Python 3.9 REPL, and we can see the compiler in action. Let's define a crude Python function that divides numbers in half. So we'll take an input of x and we'll return x divided by 2. So once you declare this function on the REPL, CPython will have compiled it and stored the code object in the dunder code attribute of the function object. You can disassemble the function into CPython bytecode using the dis method in the dis module. If you use Pyjion, you first need to import the Pyjion package and then enable the JIT compiler. If you execute the half function, the JIT will kick in and compile those Python bytecodes into machine code. Pyjion uses a hidden field in the code object called coextra to store a dictionary of attributes of its JIT compiled state. This includes the binary instructions for the compiled function. You can see the status of this by using the info function in the Pyjion module. This result tells us that it has compiled the function, it's executed once, and that the PGC status is 1, which I'll come to later. I've also included a disassembler into Pyjion, so you can see both the ECMAScript instructions as well as the assembly. You can seal the CIL instructions by using the pyjion.dis module and then calling the dis function and passing it the function object. The method calls in IL are referencing Python C API, so Pyjion will use your operating system's ABI to call the Python 3.9 C API where required. In the case of this half function, it will call the pynumber_divide, which is part of the C API, because it has no idea what x is, so it's just going to say, right, I assume it's a number, and I'll just do the division operator. You can go a level deeper and disassemble the compiled machine code into x86 using the dis_native function. If you want to use an external disassembler, you can dump the compiled binary code using pyjion.dumpNative to disk and then load it directly using a tool like Hopper, for example. So a function that divides numbers in half is pretty unimpressive. So let's try something a bit more interesting. This is a dead simple Flask application, and I've bundled a WSGI middleware with Pyjion that all it really does is when it initializes, it enables the JIT. So you can use it with frameworks like Flask and Django, and if you've deployed it with a web worker, a WSGI worker, like GUnicorn, for example, it'll enable the JIT compiler on your WSGI workers so that your web application, your routes, your functions and everything will all be JIT compiled. So once you've added this WSGI middleware, just use Flask as normal. So if we start up that script, right, and we can see that's running and listening on the port, and Flask is working as normal. So this required absolutely no changes to the existing code, other than obviously to import the WSGI module, but that can be done once at the application level. You don't need to decorate any functions, you don't need to change any functions. Your existing application should just work. So in this demo, I skimmed over a couple of things. Pyjion works by attaching a special JIT object to code objects. This is actually permitted per PEP 523. This isn't a hacky thing that we've come up with. This special object contains the compiled binary for your function, as well as some other handy data. CPython is still the thing that parses the code. You don't need to worry about whether the syntax will be compatible. Pyjion never reads the code. It works at a bytecode level. Pyjion compiles the bytecode from Python 3.9 into machine code. When you enable Pyjion, it tells CPython that Pyjion will now evaluate frames. So after Pyjion has been enabled, Pyjion will now evaluate all frames regardless of whether or not they have been JIT compiled. If it detects that the function hasn't yet been compiled, it will compile it in line. So this sounds pretty awesome. You saw that assembly code on the screen, so this must be ridiculously fast, right? Well, sadly no, at least not yet. The JITted code you saw is still calling the CPython C API, and the ceval loop is also compiled code. So the C compiler does probably a much better job actually of writing assembly than I would. So in terms of performance, it doesn't make a difference just to call the same API and have it JIT compiled. JIT compilers are faster only when they can make optimizations. So far, Pyjion has 15 optimizations that I've written, and I think when it's really pushing the boundaries, that number's going to be more like 100. All of these optimizations are patterns that can be observed with a code object when it's compiling. So Pyjion uses them to emit faster code which is still compatible with the equivalent CPython code. So as an example, let's roll back to nbody. I'll show you two optimizations that make a dent on the execution time when you use Pyjion. The first is really simple. Pyjion will notice that when you access an item in a list or tuple using a constant index, like here the number 0, 1, instead of using the pylong object for the index, it uses the much faster CAPI method for getting an item out of a list or tuple using a C integer. The second optimization is one I talked about at the beginning. When Pyjion notices that a statement uses two sequential mathematical operations on a float or long, it will keep the carryover value in its native type instead of constructing a new Py object. This takes effect for in-place operations as well, like these in-place additions and subtractions. The result of the right-hand side of the statement is kept as a native C float and the additional Py object is never allocated. So these aren't massive improvements, but they're patterns which I've observed in a lot of other Python code as well. So they don't just apply to nbody, they can be used for a number of different scenarios and actually work really nicely in a general purpose JIT. So one of the biggest challenges any Python optimization is going to have is trying to establish what type things are. So I'm working on a feature at the moment called Profile Guided Compilation, or PGC. The concept is that Python is really dynamic. It's very hard to determine the types of variables. However, the types at particular opcode positions don't tend to change much between executions of a function. If you execute a function 1,000 times, and every single time you send it a string and it works with strings, let's optimize it for strings. PGC doesn't interpret the AST like other typing tools, it's a profiler. So when you run the JITted function the first time, it compiles some probes into the machine code. These capture any types that Pyjion is particularly interested in. When you run the function again, it will use the profile and then start to make some assumptions about what it can and can't optimize. The PGC state is either uncompiled, which means the JIT compiler has never seen it before. The second stage is to compile it as a generic function with probes, which then basically emits the profile data. And then when the function is executed again, it will see that it has the profile data and it will recompile the function and then include any optimizations that it can make. You can see which stage it's at using the pyjion.info function that I demoed earlier. So let's take another example. This is a simple function in the Django source code for listing static files for a particular storage location. The first time it runs, PGC says, hey, self.locations is a list, self.storages is a dictionary, and then when it recompiles the function with the PGC profile data, it says, okay, let's optimize that. In case the types do change, it compiles a type guard to inspect the value at runtime, and if it isn't what it was expecting based on the profile data, it will default back to the generic path. So coming back to the n-body algorithm, I'm actually currently getting about a third of the execution time in Pyjion compared to CPython 3.9. Other benchmarks are showing promise are the Pfannkuch and the float benchmarks, which have around 20% speed improvement at the moment. My philosophy is that anything below 20% isn't worth the effort. So I'm looking really much higher than that, looking to see if we can get multiples of performance off this. So in conclusion, I'd love some help on this. JIT compilers are really fun to work on, and there are at this stage thousands of tests, so you can see all sorts of different scenarios and how this can be worked and used. I think the idea has a lot of potential as a drop-in module to optimize CPython and optimize code which would really benefit from a JIT, and then have a transparent effect on code which doesn't. And lastly, the more I look into this, I'm finding problems that the PyPy project has already solved. So check out PyPy and see whether your code works with PyPy. I think they've done a brilliant job already. There's a lot of brilliant science and research that's gone into PyPy and their JIT. And it can make a drastic difference to the performance of your code already. So the documentation for this project is up at pyjion.readthedocs.io, and the source is on my GitHub repository at github.com/tonybaloney/pyjion. If you want to understand more about CPython's compiler, the eval loop, memory management, I cover all of this in my CPython internals book, and you can follow my blog on my website for the latest on what I'm working on, or follow me on Twitter. Thank you and enjoy the rest of PyCon.